Okay, welcome to the webinar, everyone. Thank you for joining us. Today, we're going to be talking about case toll analysis within IP software, IP being Interactive Petrophysics. I'm Ross Brackenridge. I'm one of the product managers of IP software. My specialist area is case toll, funnily enough. This is the first of monthly webinars we're going to be doing, which are going to focus on different areas of different specialized areas of IP. So if you look out on LinkedIn or wherever you heard about this one, you should be getting invites to some others. So analysis agenda is we will give a bit of background and objectives of case toll logging. So I realise there's probably quite a mix of people on the call. One's very experienced in case toll, others maybe just here to learn a bit more. Then we'll talk about the IP's case toll solution. Within that, we'll kind of skip through all the different functionality from data management, well integrity, monitoring reservoir fluid saturations, production monitoring. During the reservoir fluid saturations, I will break out of the slides and go into a live demo of the carbon auction module. I chose that one because it's our newest module out of all these, so it should be relatively new to everybody on the call. Then we'll talk a little bit about integrated analysis, and we'll summarize and have questions. Now, you are all muted at the moment. What I would like to do is, if you could, we'll just go through the presentation first, and then we'll have the Q&A at the end. I'm not going to. Well, we're not planning on opening up the mics. What we would like you to do is there's a Q&A button within Teams. If you go in there, you can type in questions. You can do that throughout the presentation or wait till the end. And then at the end of the presentation, we will select a few questions, answer those. If I don't get onto your question, please don't worry. I will personally respond to that after the webinar. And just to let everyone know, we are recording today's session. And it will be made available on our YouTube channel afterwards. Okay. So a bit of background. Who are Geoactive? So Geoactive is the name of the company I work for, and there's also the owners of Interactive Petrophysics and Interactive Correlations. It's a new name, it's a new company name we've got, so you might not have heard of it before. But although it's a new company, there's a lot of history behind this. The products have been, well, Interactive Petrophysics has been going for sort of 25 years. And many of the actual team that work on the product have worked together for many years. So although you may have known us by some different names or company names over the years, we are very much the same people, same products, and it's a new era. These are the backers of the new company, TSS and Vela, who are ultimately part of Constellation Software. But we very much work as a sort of independent entity. What is IP? IP stands for Interactive Petrophysics, so it's an industry-leading subsurface data interpretation package. It's most known for doing open-hole interpretation, so open-hole petrophysics, calculating porosity, clay volume, fluid saturation, and much more. It does that very well and has established itself as a global leader in doing so. So although it started off just sort of in that area. Over the years, it has expanded into these other subsurface disciplines. One of these being cased hole that we're going to look at today. By spreading out into these other areas, we're no longer a product that initially was going to use at the exploration or appraisal stage of a development. It's now a product that's used right throughout the life cycle of the well. So multidiscipline for the life cycle of the well. I'm just going to turn my camera off now that I've done this sort of introduction, if that's okay. Okay, a bit about cased hole. What do we mean by cased hole logging? Well, slightly different to open hole logging. So open hole logging is when we've just drilled the well. We use wireline tools to go into the well and take readings directly from the formation. The only thing between the tool and the formation at that point is borehole fluid. And at that point, we're really trying to find out where is the reservoir rock, how much reservoir is there, what are the reservoir fluids, how much is extractable, how easily would it flow out of the well, these type of things. That's what we're trying to get from open hole tools. But then once the well is completed and brought on to production, you will then have a piece of casing in the well, a steel pipe. And then behind that, you will usually have cement. You'll have perforations in the reservoir zones to produce the fluids. You'll also have tubing and other hardware like packers in the well. So the environment has completely changed now. But not only that, we no longer have the same objectives, do we? Because we knew where the oil was or the gas was on day one. But the type of questions we're wanting to maybe answer now is our cement providing a good barrier between zones and between reservoir and surface? Is there any leaks in the casing? Has the casing worn? Are all the perforations contributing to flow? Is there water production? If so, where's it coming from? Can we shut it off? Could we re-perforate and increase production? These are the type of things that we would want to know. So the environment's changed, the objectives have changed. So we actually need a whole new suite of technology, a whole new suite of logging tools to achieve these objectives. And some of the open hole logging tools wouldn't, well, a lot of them wouldn't work with the steel casing there. And some of them wouldn't even fit into the well anymore because there's restrictions such as tubing. Okay, so we need a whole new set of logging tools. Here's a whole variety of tool types here. So for cement evaluation, excuse me, we would use cement evaluation tools such as SBTs or ultrasonics or radial bond tools. For the casing, we would use mechanical calipers like these or ultrasonic measurements or electromagnetic tools. To measure production coming into the well, we would use production logs, simple ones or advanced ones for deviated or horizontal wells. And finally, if we're trying to see fluids in this casing in the reservoir, we would use pulse neutron tools, which can be run in different logging modes. So there's a lot of different tool types there, and obviously the logging vendors are going to have their own versions of all these, or some of all these. So it's a lot of different data types and tool names that we could be dealing with. So what's the challenges of interpreting this data? Well, Technology for a start. You know, we already talked about all the different tool types and on the market from the various service companies, all with different names. Sometimes the same technology can have different names from different companies. It can be very confusing. Historically, we would need a different software package to process each type of data set. So, for example, when I used to do case tool interpretation for a service company for many years, and I think I used 7 or 8 different software packages depending on which tool type I was doing. So that's not very convenient. There's obviously the difficulty of service companies may have a slightly unique technology that means that they can only process that data in house, which kind of means that the operators are forced to not only pay for the logging but also the interpretation on top of it. Environment data analysis is difficult when you've got a piece of pipe in the well and you're trying to see either inspect the pipe or what's behind the pipe. There are factors that can really influence how you interpret and log the well, things like what the water salinity is or the deviation of the well can have a huge significance on what tool you select and what you do with the data. And of course, there's the pressure and stress of interpreting this data. Some of these are used for some very big calls. We're talking about, is the cement doing its job? If it's not, then that can lead to some serious health and safety or environmental issues, just as damage to casing could do. So it's a very important task that we're working on, and quite often the interpretation is required in a quick turnaround, because sometimes, particularly with with cement evaluation, quite often the well site is waiting for a decision, so to decide if they can go on to the next operations or they need to do some remedial work. So time is of the essence as well. So that all leads to there's this poor guy looking a bit stressed out there. So what's our solution to deal with all this? Let's have a look. So this is IP case tool. So obviously we have IP, which is the platform, the log interpretation platform, but we also have on top of that, you can see there's a menu item for case tool. We've got all these case tool modules specifically for doing these tasks. So by having all these in one package, you can result in some big cost savings. It's a shorter learning curve, learning one package instead of multiple ones. All our workflows are designed to make fast and well-informed decisions on the data. So want to give the analyst the best chance by bringing all the information to their attention before making a decision on the data. Interactivity features throughout the workflows. This is interactive petrophysics, and you'll see as we go along how interactivity with the data is the key feature of interactive petrophysics. And also by bringing all these together in one place, by looking at them side by side, we should be able to gain more insights into the data than we would if we were looking at these data sets individually on their own in different packages. So this is a list of modules that we will talk a little bit about each of these. So the data management side of things, well diagrams, then we'll talk about well integrity, casing and cement, pulse neutron for monitoring saturation, and production logging. So because we're part of IP, before we even talk about the K-STOL modules on top of that, we've already got a very well established log data management package. You know, this has been refined over and improved upon over 25 years. We've got all the data loaders for all and exporters for all the industry standard formats. We have WITSML connector for getting live data streams. We have database links to other products. We have a whole raft of editing functions, so editing, splicing, filtering, depth matching. So you can see a GIF of depth matching in action over there. There's that interactivity. Viewing any type of log plot or cross plot or histogram you can think of. Basically, IP can display your data in that format. And calculations, you know, you can do outside of the modules. You can do maths on your log curves, create formulas. You can even create your own modules with an IP. With minimal coding, you can actually create your own modules. So on top of that, then we have the K-STOL items. So firstly, if we're wanting to talk about the K-STOL interpretation, we really need to understand firstly where the casing is and where the hardware is. So our well diagram manager allows you to build casing diagrams. It contains a database of the most common casing and tubing types. So you can go in and select the pipe that's in place and the depths that they're at. You can also put in the drilled sections and their bit size. You then get this preview of the well. But you can also do more. You can do things like add perforations, collars. You can add data. You can attach a curve to any of the pipes that might indicate thickness or casing wear or something like that. And then you can put in other bits of hardware, such as packers. You can put in any object, have it any color, call it anything you want. It's very flexible. So once you've got your diagram, what can you do with that? Well, the diagrams can be plotted on any log plot alongside your log data. So it's basically like a curve type that you just select. I want my type to be a diagram, and you select a diagram, and it will appear reference to depth that you can browse alongside your data and see where the casing is affecting the log response. There's another one on a log plot with the data perforations displayed. We could also have mini cross sections here. You can see on the log plots. Then you can have full cross sections of the casing with statistics on it as well. And we could even look at it in 3D. So in this case, we've zoomed into this area here. We've right-clicked, launched the 3D viewer, and you can slice open the casing, you know, to look at the internal tubing or casing as well. So you can see we've got some wear in the inside tubing. So we know where the casing is. What about if we're wanting to do a casing inspection? Well, so we've got a casing inspection module which can inspect the casing for damage, wear, pitting, leaks. Any of these things can lead to inefficient well production or serious HSE issues. So the logging technology we would use for these are multi-finger calipers like this here, or ultrasonic or electromagnetic devices. They can all be used to inspect the casing, but the raw data from these tools it really requires some processing before you can really make a judgment on the casing condition. You also, there's some, with casing data, you'd really want to have certain ways of visualizing the data. You don't want just to look at, if this is a 40-arm caliper, you don't want just look at 40 curves side by side. That's not going to give you a good interpretation of what's happening. So visualization is a key. So here with the casing inspection module, this is it up here, and it's a very intuitive workflow that you just go from left to right across the tabs, doing your setup, you're bringing in your completion diagram, picking collars, doing data QC, and then applying some corrections to the data. Why do we need corrections? Well, this is an example here that we have raw data on the left and processed data on the right, and you can see the difference between the two. This data set has some typical problems. You can see this, it looks like the casing is almost, buckled. It looks like it's kind of wobbling around. That's not actually real. That's because the tool will be sitting in the center, but it might be slightly off center, and the tool is also turning as it's going up the well. So it's actually the tool that's kind of wobbling around slightly as we're logging, and that gives it the appearance that the casing is buckling, but it's not. It's an artifact of the logging. What else is going on here? There's some arms that are kind of sticking out further out than the rest of them. There's ones that are kind of sticking inward. So it's quite often that we might get arms that get stuck during logging. Need to deal with those. There's gaps. So we have null values. There were some spikes on this data as well. So you can see, because of the offset and all the curves, the min, max, and average of these there's quite a big spread on them. But once we've applied all the corrections that we have in here, you can see a much more cleaned up data set. It almost looks completely different. That's because we've taken out all those issues, and what we're left with is the real data, the real response of the casing. So at that point, we can then start reporting on the condition. So features of the module, then we've got this, as you've already seen, this kind of interactive spinning log plot, which is really nice. We developed that especially for casing inspection. So it's kind of a combination of like a 3D viewer, but it's actually part of the log plot as well, which is good. We can make these color maps. We can then, so each joint gets a grading. You can decide how many gradings you want. In this case, we had 6, but you can have up to 10 different colors or grades. And you end up with a report that tells you for each casing joint, it's giving a statistics on it and a condition. And there's some stats on how many of each condition we ended up with. We also got the cross section that you can do for every joint, and that'll give you the min, max, and average radial kind of diameter of each joint. And that report can be exported to a Word document or a PDF. So that's the casing. What about the cement? Without being too dramatic, we know there's been some serious incidents over the years, partially, not just because of the cement, but partially due to poorly cemented wells. So, it can cause serious problems if the cement is not in the place that we intended it to be. So we run, after a cement job, we would always usually run a cement bond log now to inspect the condition of the cement. But these CBL logs, they've kind of had when years gone by, they can have a reputation of being slightly confusing and a bit inconclusive, so you could put one log down on a table in front of 5 people in a meeting, and they all might have a slightly different interpretation of what they're seeing. You really need to take the raw data and assess it to really determine what the strength of the cement is and the distribution of the cement. And that can be very challenging if you try and do that manually, looking sort of depth by depth and maybe looking up log interpretation charts, marking where where all the different parts of the data are all responding to good cement. So when we say good cement, what do we need from that? Well, we need a good bond between the outside of the casing to the cement. We need a good bond between the cement to the formation. We need good vertical consistency. And we need good circumferential coverage. We want to see that cement all the way around the outside of the casing. What we don't want to see is kind of partial cementing, or even here where we've got most of it is cemented, but we've got what we describe as a channel that can allow fluids to travel through. So we don't want to be seeing that. Or if it does exist, we need to know about it. So it's really about taking the data and going through these steps and checking it for the criteria we just spoke about. About the casing to cement, the cement deformation, the circumferential coverage, looking out for channels. It's only when we've approved all these criteria on a particular depth that we could say, okay, at this depth, we think the cement could be providing a hydraulic seal or a barrier within the annulus. So that's what our module does. A bit like the casing inspection module. It's a intuitive workflow that we go from left to right. Completion and collars and things are the same, but then we go on to creating our own cement maps, and we can do this for almost all of certainly the most commonly used cement evaluation tools on the market. So yeah, it allows us to make a fast, informed conclusion. We end up with a results table like this. This time, we're not talking about the casing, we're talking about the cement, and we're giving this sort of traffic light. So it's showing where we met all the criteria, we get a green light. Where we failed all the criteria, we get a red light. When it's partially passing, we get that amber color. Other features, well, we can normalize the raw data before we start the interpretation. We can obviously create our own color maps. We're not just relying on the ones that we get from the field. And we have interactive parameters that we're allowed to, as we move these cutoffs around the cement map updates real time. We can see how that changes our interpretation. There's that traffic light at the end there again. And we've recently updated quite recently, updated the module to have the most workflows for the most advanced tools, like the Schlumberger Isolation Scanner and the Baker Hughes Integrity Explorer. These are ones that are typically used when we have unconventional cements in place. That's just the results tab there, filtered to show just where all the good intervals are. So we've looked at the casing and the cement. Let's look at the reservoir now. So now we want to know what's the reservoir saturations. Have they changed over time? We know where the oil or the gas was initially. Is it still there? So we use pulse neutron tools to do this. We do that because neutrons can be fired and travel through casing and cement. And as the neutrons interact with the formation, they emit gamma rays, and we can pick up the gamma ray counts on the tool here as well. And by looking at those gamma ray counts, we can kind of tell certain things about the formation fluids. There's two different logging modes that these tools can be run in. That's sigma mode for when our reservoirs have highly saline water, or carbon auction when we have low or mixed water salinities. Raw data is really almost impossible to interpret without doing an interpretation and trying to compensate for the environmental factors. It's heavily influenced by the borehole environment. And also key inputs, although this is cased hole interpretation we're doing, the porosity and clay volume are from open hole logs are a key input into the interpretation. So our solution for this, well, before we actually talk about the cased hole modules, remember again, we're in IP. So before doing that, we could, if we want, create our own clay volume and porosity. There's a variety of ways we can do that in IP, from a very advanced workflow to a more sort of simple workflow like this that you might be more comfortable with if you're a cased hole analyst. Yes, this allows you to calculate, do an open hole interpretation, use these inputs in your interpretation. Typically, as a cased hole analyst, if you work for a service company, you're given clay volume and porosity from the operator. You've just got to assume that it's correct. You know, you've no real way of telling if it's good, bad, or indifferent. So, but if you are in IP, you have the option of being able to look at those yourself. Then we've got the modules themselves. So we've got two separate modules, one for the sigma analysis. It uses a material balance equation, takes the cased hole and open hole data, put in some parameters, and you calculate cased hole water saturation that you can see here. Now, in that equation, there's a couple of parameters that have a really big influence on the result, and those are the sigma value of your water that you put in and the sigma value of your clay. And what's quite neat about this module is that, like other things in IP, it's interactive, so you can let the data try and help you pick these points. So here you can see we're picking a sigma clay value by doing a regression to 100% clay here. So that number is adjusting that is real-time updating the model and updating the saturation result. We also have a time-lapse version of that module. So if it's not a standalone analysis and you actually want to calculate the difference between two different logs logged at different times, different years, then we've got a module for doing that direct comparison. But then if you go into reservoirs that have low or unknown water salinity, then you need to log the tool in carbon auction mode. Now, until recently, there hasn't really been an off-the-shelf interpretation module for interpreting these. So it's really been the service companies that have had to provide the interpretation of these, and that a lot of times the operators are kind of unable to do that, which can be a frustration. But now, just this year actually, we created a module for doing carbon oxygen interpretation. I'm going to show you a demo of that. Before I do, what's the workflow that we designed the module around? Well, first we need to understand the petrophysical properties of the well. You know, we need to know what our porosity, our clay volume is. And then we need to understand the cased hole environment. What casing size are we in? What borehole size, fluids are in the borehole? All this is going to affect the log measurement. So then, depending on what tool we have, how is this particular pulse neutron tool going to respond in this environment? You know, if we have water or oil response, what's it going to look like in this environment? We then take that predicted model and the real data, overlay it, fine-tune the model, and then ultimately get a cased hole water saturation. So that's the workflow. Let me just open up IP. So for those of you who haven't seen IP, this is the user interface. You can see the menus down the side here. So we've got all the sort of data management stuff we talked about up at the top here. And then we go into sort of specific groups of modules. We're in the cased hole area. So here's all our cased hole modules that we can launch here. This is our data browser. So you can see we've got a well in our database. This is the Volve, a Volve well that was released by Equinor. So in here I have curve set with some carbon oxygen data. It's a Schlumberger tool. I then have open hole data as well. So I've gone in here and I've launched carbon oxygen module. This is the module here. So we've got the setup of what the curves coming into the module and curves going out of the module. IP, like any IP module, it will go looking in your database to try and find the relevant curves automatically. In this case, it's gone in and it's found most of it's found the CO from that set, and it's found the porosity from this set. A few other reference curves we're bringing in. So I can actually see that it's actually picked up the wrong gamma ray here, so it's picked up the open hole gamma ray twice. This one should be. So you need to check that it's got them all right. But if there's one or two that needs to be adjusted, you would do that now. I've created a new curve set called results, and I'm going to output all my all these curves into that results set. So ultimately, I'm going to try and calculate this, which is a carbon oxygen water saturation. So that's a behind casing water saturation. All these other curves are created as part of the process for calculating that final curve. So that's the data coming in. The logging environment. This is where we could put in our casing sizes and borehole sizes. Now, if you already have a well diagram, which you could have created in your well diagram manager, you can just simply select the diagram here and it'll bring on all the relevant information. So here we can see at the bottom, we've got 7-inch casing. There's actually 2 different weights of casing there. And the bottom is an 8.5-inch borehole. Further up, we've got 12.25, but the logged interval that you can see down here is really just kind of covering this bottom section here. But every time we have a change in the logging environment, we need to change the model. So if we have a change in that, the model needs to change where there's a change in the world environment. So what we do at this stage is we can choose processing zones, if you like, from either the borehole size or the casing. I've chosen the casing. If I say create, there we have created two different parameter zones because there was two different casing weights. So it's decided you need two different ones. So that's all we need from the casing diagram. We then go on to the model. So the model, this area is like a model manager. So this has been a sort of sticking point for carbon auction analysis in the past, is what your response model is. We do plan, we've already been speaking to some of the logging vendors about getting some of their models into the module. Or if you have run some carbon auction data, the logging vendor should be able to provide you with a log response chart from their tool planner. So if you do have that, you can then go in here, you can simply type in, this is porosity, this is oil water response. So you can go in and just recreate the diagram that you've, the fan chart that you've received from the logging vendor. You can put in as little or as many. You need at least 2 points to make a line, but quite often you will get a tool response chart that actually has up to 9 values on it for different porosities. So as I say, you can recreate that model in here. If it's not already in the database, you can recreate the model yourself. You can have linear or curved models. But if you don't have anything to work with, you can take one of our standard sort of generic models. So in this case, I've got sandstone. I'm going to take this generic sandstone model here that's got an oil and water line. I'm going to use this, and so I'm going to apply that to my processing zones. So I haven't done anything that interferes with the interpretation until I say apply this model to the processing zones. So now we've got enough information to run the module now. So let's run it, make plot, and here we can see what have we got: casing, open hole data here, CO data. This is our carbon auction data laid on top of the model response. So for every porosity depth, we get a new kind of fan. This is our, if it was going to be oil bearing, the pink curve, the CO curve, which is pink, should be sitting on the oil line, which is green. If it's water filled, it should be sitting in the blue line. I'll come back to this track in a minute. And then we have water saturations calculated comparing to what was open hole and cased hole saturation. So we have an answer, but not quite happy with this answer yet because the CO data is kind of stepping out of the model sometimes. So we want to fine tune that, and we can do that by opening this cross plot. Let's look at porosity versus CO, and I can, here's my model overlaid with my data. So I can adjust this model till I think I'm getting the best fit for the data. So if I think I'm not quite catching some of these points here, I could reduce that here. A good way of normalizing this is if you have a zone that you knew was wet previously, you just try and normalize it in that wet zone down here. So you're matching your open hole and cased hole saturations. So once you think you've normalized it to a wet zone, the other thing we need to correct for is clay, because clay has carbon in it. Carbon auction versus clay, and this point here is our 100% clay value. So I'm looking for a trend in the data here to do a regression through to sort of 100% clay. As I do that, if you keep a look at this track here as I'm doing it, if I move that up and down, you can see that model is updating, and the more clay I put in like this, it's starting to look, the model is starting to follow the data a bit more. So a lot of this bump on the CO was actually to do with clay, not to do with more oil. So there we have, that's the two things you would really kind of tinker with, and then you should have a reasonable case to water saturation. In this case, we can see the bottom two zones, which were oil bearing, are now water filled. At the top zone, looks like there's still hydrocarbon in that top, so perhaps we can go and perforate that zone to increase production. Okay, that was carbon oxygen. Checking how am I doing for time? Are we have a little bit? Okay, so we've still got 12 minutes. Okay, so if I just go back, I'll quickly go through the. We're going from looking in. So I'll just skip through that. We've seen that already. We've gone from looking behind the casing. Now we're actually looking at what's inside the casing. So we're looking at production log data, and we're trying to measure which fluids are being produced by which perforations and the volume of that production. So one of the main challenges is depending on what the deviation, if you've got a vertical, sorry, a horizontal, no, vertical, right the first time, vertical well like this, you can use a kind of standard production logging tool because the flow in the well is basically kind of symmetrical. So by measuring the middle gives you a good indication of across the bowl. But then if we go into deviated or horizontal wells, we need to change the technology we're using to array tools that have sensors placed either up and down the borehole or around the borehole like this. So for conventional tools, this is our PL module. PL is a big, it's a big task. There's a lot of processing involved, a lot of data management involved. So we've got a lot of the data management stuff within the PL module because it's quite specific for, because PL we do a lot of different up and down passes. So we've got ways of loading all that data in quickly, editing it, averaging it, etc. And then we work through the workflow, calculating velocities, hold-ups, and ultimately flow rates, like we have here, showing which fluids are coming from which zones. But then if we go into the using the advanced tools and deviated horizontal wells, the interpretation had to completely change, really. It is still the same module, but the workflow was pretty much rewritten specifically for this scenario, because now we're not looking at averages in the middle of the borehole. We really need to look at the full borehole and use the data that we have from these advanced tools like Schlumberger FSI and the MAPS tools that are used by Baker and Halliburton and other companies. So what we do is we break the borehole into different segments, and in each segment we calculate a velocity and a hold-up, and ultimately a flow rate for each segment. We can then total them up to get the total flow from each zone. In this case, we saw a lot of gas in the borehole and high velocity in the high side, and then we saw lower velocity and water on the low side. So at first glance, this looked like obviously just gas and water being produced, water traveling on the low side. But if you actually look at the data here on the low side, the velocity is actually showing negative. So what's actually happening is the gas is moving up the well very fast, being producing gas and a little bit of water. It must be carrying quite a lot of water with it, but not all that water is reaching the surface, and it started dropping back down. And this is actually the water running back down the well that we're seeing. So it's only by looking at this, breaking it into these segments that you can get a true representation of what's happening in the well. So that's production logging analysis, a little bit about integrated analysis. We're bringing all this data together. So here's just a hypothetical example of a scenario that could occur. So we have a well that's been up till now producing a large amount of oil and gas, a little bit of water, so everyone's been happy. But more recently, the oil production has decreased, as has the gas, and we've started producing a lot of water. So we run a production log. And the production log tells us, is quite conclusive, that it's said, okay, all we've got is oil being produced from this perforation. And mostly the bottom perforation is producing oil as well, but the bottom of that perforation is producing water. So that's where our water is coming from, that reservoir zone here. Or is it? If we actually took data, had our open hole data, production log data, if we take the temperatures from that as well, casing inspection data, cement evaluation data, and pulse neutron data to get brine casing saturations, we start seeing a slightly different story. We notice that there's big spiking in the cased hole gamma ray, which could indicate scale buildup. Now, scale buildup happens when you have water flow in some cases. Now, we don't have water flowing in the borehole, so that would indicate maybe there's something happening behind the casing. The temperature between shut-in and flowing, this spread here, also indicates that there's likely to be something flowing behind the casing. Casing's in good condition, so we don't have any leaks to worry about. But look at the cement. The cement has what looks like a channel coming from that bottom perforation deeper into the well. If we look at our pulse neutron data, we see that actually this zone looks still oil bearing. This bottom zone looks water swept. So what we're likely to be seeing here is actually something like this illustration that's showing the water is actually originating from this zone, but it's traveling up the back of the casing through the cement into the borehole. So it's only by looking at all the data, the different cased hole data sets together alongside open hole data, that we really get that understanding. Okay, I'm a little bit over schedule there, but oh yeah, sorry, I forgot my summary. That we've got a package here that can do a wide range of cased hole data types all in one package. Fast, intuitive, and interactive workflows to answer all those objectives the various objectives that we were talking about. Gaining greater insights with cased hole and open hole together. Big cost savings and shorter learning curve for users using the program. Just remember, cased hole is one of 8 bundles or flavors of IP, if you like, and watch out, in the coming months we'll be doing other sessions on each of these topics.